welcome to this year's Baker Hughes Masterclass. We'll be covering carbon capture, utilization and storage. I know some of the girls who did the program last year did their project about this, so they might know a little bit about it already, but for the next hour, we're just going to be going through what the greenhouse effect is, activities that, add to it, carbon footprint of activities that on the internet, and say how, what different things have an impact and stuff like that, what we can do about climate change, and then we'll get into the CCUS topic about what it is, how we do it, different things like that. First, we're going to go through the pre-work activity that you should have already done before the session. So it was 3 questions based off of the video that I sent out about 2 weeks ago. So the first question is, how does the greenhouse effect benefit the Earth and how could it hurt the Earth? So it helps keep the planet at the right temperature to allow for life, everything like ecosystems and everything to maintain in place. However, if there are too many greenhouse gases, which is the problem that we're experiencing at the moment, the Earth can get too hot and then it can have more of a detrimental effect. The name of the jacket of gases surrounding the Earth is the atmosphere, and 3 greenhouse gases are carbon dioxide, water vapor, and methane.
Wonderful. So I guess at this point we can hand over to our masterclass presenter, which is Alexandra.
Good morning, everyone. My name is Alexandra, based in Aberdeen in the UK. I work for Baker Hughes company, which is an energy technology company. The idea is that we try to make sure that we support with energy generation, which is safe, which is reliable and affordable. So the vision of our company is just to make our life and the life of people and the planet a little bit better. And we support with a lot of initiatives associated with the energy clean out, with energy transition, and one of the main directions is the carbon capture and storage, which I am in charge of for our region, so I'm going to talk about that today. But before we go to CCUS, I want to give you some background about why it's important and why we talk about that today. So let me start from the greenhouse gas effect. I think you already did your homework exercise. You are aware what greenhouse gas effect is, but the idea is that our planet warms by sun. So sun warms the crust, the surface of the planet, which makes our life on the planet quite good. The idea is that it's usually done during the daytime. So whenever it becomes night, it means that the Earth starts to emit the warmth or the energy which was provided by sun. In order to stop this process, we have special greenhouse gases, which is carbon dioxide, water vapor, and methane, which actually absorb partially this emission from the Earth to keep the Earth warm. By that, the average temperature on our Earth is around 14 degrees Celsius. If we didn't have this atmosphere layer of these 3 gases, the average temperature would be minus 18 degrees. So it wouldn't be possible to have any life on our planet. So technically, it's good to have these gases on our Earth. But the thing is that when we have too much gases, it might cause the Earth to warm up even more, and that also have its own consequences. You probably have seen a lot of news about the hurricanes, about different fires happening globally, and all of these things are actually the effect of greenhouse gas. So it means that technically we have to control these emissions to make sure we can continue our safe and good life. I hope so. Just to give you some background information why it happens, because for the millions of years, the average level and volume of these greenhouse gases was quite stable before the mid of 18th century when the Industrial Revolution started. So just as a statistics, the amount of CO2 in atmosphere from the middle of 18th century to nowadays increased by 50%. And for the methane, it increased by 150%. The good thing is that the overall cycle of methane in the atmosphere is just 12 years. So even though the volume increases from year to year, the cycle is short. So it means that we can somehow maintain the amount of methane in the atmosphere. But with carbon dioxide, it becomes more complicated because the general cycle of carbon dioxide absorption, the Earth cycle, millions of years. It means that if we do not start controlling that volume of CO2, that will lead to increase of temperature on our Earth. And you already heard some news about the Paris Agreement and that we expect the temperature to rise to 2 degrees Celsius in upcoming future. It sound not that much, but in reality, it affects the whole biosphere, atmosphere. It affects all our lives. So that's important to control that. Now, I mentioned about the Industrial Revolution. So the idea of Industrial Revolution was to start using the fossil fuels across the globe to generate heat, generate electricity, make sure we can produce more goods for people, growing population. So the idea is that whenever used with fossil fluids, we burn them in order to generate the energy. And while that combustion process, we have heat, we have water, and we have the carbon dioxide. Again, majority of the carbon dioxide generated by industrial activities, as I mentioned, fossil fuels burned, but this is caused by power plants, transportation, aviation, and all other activities. Even waste produces some carbon dioxide. Generation of plastics produce carbon dioxide, all of these activities. And of course, the main step of controlling the carbon dioxide is to control this industry. But the thing is that even in our daily activities, we also produce a lot of carbon dioxide. And when you compare the volumes, you might feel like, oh, it's just a tiny piece of what I am personally producing. But in reality, considering 8 billion people living on the planet right now, that also becomes a significant effect. So let me give you one of the simple examples. Whenever you go to school every day with your parents by bus or a car, you already produce some emission. Whenever you decide to buy something in store or buy some food, as a result of agricultural business, that's the matter of producing carbon footprint as well. So every single activity, even taking the shower in the morning when when you're using your boiler for 10 minutes, it's already producing some carbon dioxide. And interestingly, even social media and all social activities which you have using the internet, they're also producing some carbon dioxide. So what I want you to think about right now is just to think how much carbon dioxide we actually produce when we send one single message to our friends. And you might also think how much carbon dioxide we produce when we send one single email. For example, we exchanging emails during our life, during education process or at work. Just I will give you some time to think about that. What is the footprint of every single activity here? Okay, but I will tell you one thing. Whenever we send one single email without anything attached to it, we produce 4 grams of CO2. Whenever we send any single text like WhatsApp message or SMS, we produce 0.014 grams of CO2. Now you can think, oh, but it's almost nothing. But imagine the amount of messages we send every day to our friends, colleagues, parents, send emails to council, to different organizations. So that's a significant volume. So if we go to the next slide, you will actually see that every single activity in social media releases some CO2. Can you please? Yeah. So imagine You do your activity at school, you send a couple of messages during break to your friends talking about some stuff, or you decide to send a selfie to someone. So one single selfie produces 50 grams of CO2. Or after school, before you decide to go to do your homework, you decide to scroll social media and go to Instagram to see what's going on. So half an hour scrolling produces 83 grams. Just half an hour. If you multiply that by 365 days per year, considering that you spend only 30 minutes on Instagram, you can actually see the number, which is actually more than 33,000 grams. For sure, we don't spend just 30 minutes on Instagram. We do it much more. We send much more emails. Or if you decide, by the way, to do some streaming on Netflix, 33 grams per hour. Of course, it's not just an hour. It might be minimum 2 hours if you decide to watch some movie. So behind every single activity, we have the carbon footprint. That's why it's so important to control and maintain not only industrial level of carbon emissions, but even during our daily activities. That's important to think about. Now, if we switch to the next slide, yeah, we actually can see how we can control our climate, because at the end of the day, as I said, all emissions lead to increase of temperature on Earth, and that affect the entire biosphere and the quality of our own lives. So what we can do here? Option one, renewable energy sources, solar, wind, wave energy, geothermal energy, usage of hydrogen, a lot of discussions about that. One minor thing, there is no really clean energy. Even renewable energy has its own footprint, but it's very small comparing to standard fossil fuels energy generation. So that's one of the directions we can do, and it's widely used in the UK as well, in Scotland. Whenever you travel, you can see a lot of wind farms, for example. So that's one of the ways we're currently doing. Second is to plant trees, because trees absorb CO2 and they release oxygen, so that can help us. But imagine how many trees we have to plant in order to maintain the level of CO2, which is already increased by 50%. Enormous. So what we need to do and what we try to focus on as an industry, apart from renewable energy, we're focusing on carbon capture and storage. This is one of the key mechanisms to maintain the carbon emission level. So how we do that? If we switch to the next slide, let me give you a short introduction about what carbon capture is. So you might see a lot of literature where you will find the abbreviation CCUS. So CCUS stands for carbon capture, utilization, and storage. In industry, we call it the entire value chain. So the idea is that we capture the carbon dioxide from fuels, from atmosphere. Then once we capture that, we can transport it to certain locations. You can clearly see that on the slide. So we have certain facility. Let's imagine this is the cement plant, which emits a lot of carbon dioxide. So we can capture that carbon dioxide, and then we can transport it through different options to special facility. And from that facility, we can already decide what we're going to do with that carbon dioxide. We can send it further to store it somewhere. For example, we store it subsurface, usually offshore or onshore at specific depths in certain formations. It's like a sponge type rocks where we store the CO2 for millions and millions of years. So that might be number one option. Or number two, we can utilize this captured CO2 in petrochemical industry, for example. So as I said, three main steps: we capture, transport, and then we store. So let's start from the step number one, which is capturing. How we do the capturing, and that's one of the initial steps. It's very difficult process which engages chemistry and physics. And there are different types of capturing techniques. There is no one single technology which is fit for purpose to all industries. Usually there are four, as I mentioned, types. So first thing is that we can capture CO2 before combustion process. What does it mean? It means that whenever we have any fuel, before we burn it in order to generate the energy, we exclude CO2. So we try to capture it. How we do that? We try to make sure that our fuel is converted to gaseous mixture of hydrogen and CO2. So hydrogen goes through the process of combustion and we separate CO2 from that. So that's number one. So CO2 doesn't join the party today. Option two is to do it post-combustion. So what we do, we actually take the fuel, we burn the fuel with an air, with the oxygen within the air, and then we use different chemicals that might be different sorbents or solvents, for example, chilled ammonia or mixed salt processes in order to exclude the CO2 from the system. So the CO2 has the reaction with the solvents, and then we have the separate heating process in order to exclude CO2, and captured CO2 is already transported further. So it's like it joins the party, but then we say you have to go away. The third process is the oxygen combustion. It's quite similar to what we do in terms of the pre-combustion and post-combustion, but the idea that we don't use the actual air, but we first make sure that we use the entire oxygen out of this air. Why it's important? Because air is the mixture of different gases, and whenever we burn the fluid within this mixture of gases, we usually have different mixtures, and we also have to remove them somehow. So we just use clean oxygen, we have the combustion, we generate CO2 and hydrogen, and then CO2 is removed. And the last one is a direct air capture. So it means that you can imagine it's a huge vacuum cleaner. So we absorb the CO2 from the air directly from air. We don't need to have any facility. We absorb that from air. We use special filters to absorb CO2. The clean air goes back to atmosphere, and then we heat the filters to actually exclude CO2, and then we can reuse them. So 4 different technologies. Now, as I said, every technology has pros and cons, most of them associated with chemical activities, volumes, pricing, but all of them are used right now. So we capture that. Step 2, we transport. The transportation method can be different. It can be pipeline, it could be some different ships, it can be road, trucks, trains. Really depends on the distance. I would say that distance is probably one of the main things we evaluate before we define the way of transportation. In most of the cases, it's pipeline, but you can often can see that we use different ships because we liquefy the CO2 to the dense phase and then transport, because it's cheaper and more efficient than using kilometers and kilometers of pipeline. So we transport that to certain location. Now we need to store it somewhere. And this is where the most interesting thing starts. So how we store, and the most important, where we store. That's the major question which the industry is looking for. So we usually store CO2, as I mentioned, beneath the Earth's crust, a few kilometers down in subsurface in information. Usually it might be the aquifer, so the where we have water, or some ways from which we produced oil and gas initially, so they were depleted because we almost soaked everything, and we can inject CO2 just in there. Was it safe? Yes, it's safe because the system is closed and we can store CO2 for millions of years. Now, in order to define the reservoir, it's just only the first step. We identify the reservoir according to the specific properties which we are looking for. Scientists and engineers are looking for specific properties. Once we define that, we need to gather as much data as possible. So we do different exploration activities. We gather geophysical data based on the physical properties. We do different tests to make sure that this reservoir which we chose is good to go. Then we construct the facility, we construct the wells, and we start injecting. So once we start injecting into the reservoir, we do the entire monitoring, because we need to make sure that our area is safe and we avoid move of CO2 back to surface through different channels. So now, when we talk about the storage, what makes it good? three main pillars and three main questions, I would say, to which scientists and engineers pay attention to. First of all, it's capacity. This is how we say it in industry. So how you can memorize it, how much we can actually store inside. This depends on the free pore space inside the reservoir. So we're talking about small pores, which are not filled with anything, where we can potentially keep CO2. So that's number one. Second is injectivity, and this is associated with permeability. And what is permeability? Permeability is about how the spores are connected. Because you can imagine the sponge. So the sponge consists of different pores. You can see some holes, and all of these holes are connected. So the better connectivity between these volume spaces, the more you can actually store inside. So that's the whole idea. You can actually see very nice animation of the permeability depending on the different formations. So as you can see, for example, in gravel, we have more connections between the pores. That's why the liquid can actually go faster. And the last one is the containment, which is the integrity of the system, how the system is safe or not. This is usually the idea of having very good impermeable layer on top, which avoids the propagation of CO2 back to surface. So, and very important thing here is how we evaluate that. If we go to the next slide, you can actually see the entire workflow of different analysis, how we do that. And that involves different people with different backgrounds. So it's a combination of different analysis. This is geology, this is geophysics, geochemistry, reservoir engineering, geomechanics. All these disciplines are associated with physics, math, and chemistry, which mean that all the engineers, all people with different backgrounds are needed by the industry in order to evaluate that site, in order to make sure that we can do the storage in the safest way. So you can define what you would like to be in the future, choose your career and be one of these great engineers and people who will support the industry. So that's one of the things. If we go to the next slide, again, we have one question for you, because there is a one step which I didn't cover. I mentioned capturing, transportation, and storage, but I missed one thing, which is utilization. So I would like you to decide how we can utilize the captured CO2. Usually we can utilize CO2 in all the different ways. In most of the cases, it's actually the petrochemistry. So we can produce concrete, plastic, and soap. We can use that in enhanced oil recovery, so we can inject the CO2 back to produce more oil and gas. And overall, we can actually help even to plant faster. Grow plants faster in greenhouses? Kind of, but in most of the cases, it's actually the petrochemical activities. So yeah, I think that's very interesting
Good job,
question
guys.
for you. Yes. So just to summarize, again, what we need to do, despite the amount of CO2 which we have in our atmosphere, we still can be on track. And CCUS is one of the best ways to do that. Yes, we switch to renewable energy, but CCUS is one of the major things still. And even you can control the CO2 emission by doing very simple steps, controlling how you scroll your social media, controlling how you go to school every day, which transportation route you use, and all of the things. And the most important, by understanding this industry, you can choose your career pathway in the future, because we actually need smart guys and engineers with different backgrounds who will support us in this pathway. So I'm happy to hear any questions if you have.
So just from myself, Alexandra, to get things going, what is it like to be working in an industry with such a positive message? You know, how does that impact how you work?
I'm really passionate about what I do. I believe that because we were the standard oil and gas company, right? And there was a special perception, like this is the quite dirty industry. I think it's important for us to understand that we can make sure that we live better life. And considering that such huge company does these steps, it's something which inspires us a lot. And because sustainability is one of the major things, environmental sustainability with people. So for me, it's a pleasure to be the part of this change and be the one who drives this change. That's really inspiring. And the good thing I will tell you, because for engineers, it's a little bit shift of mindset, but we understand that we can utilize the skills which we learned in oil and gas industry and just apply them in the new energy. So I believe that's the most important. This is about how you can a little bit change your mind and do something better.
So we've got a really interesting question here. How do they liquidize CO2 for transport?
It's happened by decreasing the temperature. It usually goes to -degrees in order to make sure that CO2 goes to the dense phase. And this is associated with a lot of challenges because you need to make sure it's liquid. So you go to -degrees and then you revert back it to gas. So you need to increase the degrees. Plus, it's associated with challenges with the metallurgy. That's the most thing. But it's usually the matter of pressure and temperature things, mainly temperature.
Do you know which country is leading in CCUS? Is there anyone that is standing out in terms of research or progress towards doing it well?
European countries doing really great. Norway and Denmark are the ones of the leading countries. UK started doing really great. One of the first countries where we had the pilot CCUS project was actually Australia. You can read about the Chevron project for Gorgon field. If we're talking about European countries, I would say that Denmark, Norway, and UK is doing great. Spain started some activities as well. So you see that actually European countries improve a lot. Eastern Europe countries started doing some progress as well. But as I said, Norway and Denmark.
What's your personal favorite method of carbon capture?
I am passionate about, to be honest, direct air capture. I don't know why, because when I first read about it, you can have a filter, physical filter, so you can just actually soak the air, go through that filter and release the new, the clean one. This is what I was impressed by, to be honest. Plus, technically, it's simpler, at least with my understanding, to implement. Of course, I'm not talking about all the chemical reactions going on, but this is what I really impressed about.
Yes, I can certainly tell you're passionate about it. There's a couple of questions from a few different people about how efficient it is to do carbon capture.
Very good question. Without that, it's not possible to be efficient in terms of emission control. That's number one. This is what you need to understand. From industrial perspective, I think this is the balance between emission and available storage space. I personally don't feel we have enough storage space. We're evaluating globally where we can store. It's also about the logistics, how you can transport this CO2 to storage space, because it's quite costly. It might be more efficient, but we're working toward that. It's becoming more and more efficient, I would say. So far, we just started. It's just some pilot projects going on, but it becomes easier and more efficient from technological standpoint and from financial standpoint. But of course, we have long way to go. Because, for example, I will give you one thing. By 2050, I think it's 7.6 gigatons we have to store. We don't have enough capacity for that just right now in terms of the storage availability.
Really interesting. 7.6 gigatons is an incredible amount of volume. Are there any processes we can use to make the other greenhouse gases better? So, for example, methane and water vapor.
mainly with the methane. There are processes of capturing methane as well and utilize the methane as well. So it might be similar to CO2. If you know the underground gas storages, I think the methodology is more or less kind of similar. I know that in terms of the monitoring methane, it's easier because the footprint of the methane is more visible, and some companies and some industry, they actually even use some drones to maintain the level of methane emissions. So yeah, the methodologies are really available and probably even easier than CO2, I would say.
I've got an interesting question here. So you spoke a bit about where we might store this CO2. Marden High School are asking, has it ever been investigated that we could put it in space, get rid of it from our planet completely? It's maybe a little bit of
Wow.
an out there suggestion, but do you know if there's been any research into that?
Honestly, to my knowledge, no. I'm not aware of any such kind of research. What I know that there were some researches in terms of trying to store CO2 somewhere, not just offshore, but I mean using the ocean somewhere very deep, and try to do some geochemical reactions to make the carbon like a solid and store it like that. But again, this is more like the research, nothing regarding the putting that in space. What I know that there are some researches going on in terms of storing CO2 in metamorphical rocks, create some geochemical reaction out of which we actually can produce even hydrogen. Some areas are present in New Zealand, so we actually have hydrogen being produced from beneath surface because of these reactions happening, but it's quite rare case. But to my knowledge, nothing in space so far.
No, it is interesting, thinking outside the box with
Yeah,
these things and
exactly.
what else we could do. I imagine there's probably ethical implications to polluting areas
Yeah.
outside our own planet. But maybe there are options in the future as we advance and other areas can be explored. It's all research, all development. It's very interesting.
Yeah, considering what Elon Musk is doing right now, I wouldn't be surprised. That might be something to consider, actually.
Yes, it's not impossible.
Nothing is impossible. I mean, we can do anything.
So a bit of an interesting one here, which I'm going to elaborate on slightly, which is what is the most used way of CCUS, and also how close are we to actually, combating climate change? How much storage do we do and capture do we do versus how much we produce right now? Yeah. Which method of CCUS storage is the most used right now for?
Method of capturing, or
Oh, sorry, capture, method of capture.
I think there is no the one which is more used and less used. Again, that will depend on the industry. I would say post-combustion probably one of the most widely used method. Pre-combustion is also the case. Oxygen combustion, it's quite expensive, so it's not something we really use. And direct air capture is something which is more on the development stage right now. So I would say post-combustion is the most commonly used one. With regards to volumes available for storage and capturing, of course, we are not doing enough. I mean, usually annually in one of the good storage spaces, we can store 1 million ton of CO2. Multiply by 30 years of the project, 30 million tons of CO2. It's still not that much enough. But again, we are in the very early stage of the CCUS era, I would say, because for a couple of years before, it more was on research and science space. And now we finally start to the actual activities, capturing and injection. So yeah, you can actually compare. We capture around, this is what we do, 30 millions per the storage, one basic storage, around 30 million we capture specifically to store that volume in subsurface. it's not enough in terms of capturing, but again, this is the balance which we currently have. We need to make sure that we have enough storage in order to capture more, to be honest. This is a little bit win-win thing.
All right, thank you very much. So just to wrap up today and make sure you've all taken on board everything that we've covered, we're going to ask you girls to make some posters for us, just explaining CCUS, its benefits, and everything that you've taken on board today and why it's a positive thing that's going to help make the world a better place. So we've put some just examples of what you might want to cover up here. And if you could send pictures when you're completed through to the email address on your screen, we will be having our executive sponsor, Maria Claudia Boras, review them. And she's going to select a number of posters and there will be prizes as a result.